Um, so it points out here that just doing item-based filtering collaborative filtering doesn't solve scalability directly. Um, in the paper of Amazon in 2003, it describes a preprocessing approach where you calculate all the pairwise similarities between items in advance. You just do that, say at midnight. Although actually this is doesn't really matter when you do it because you're actually these sites are online 24 hours a day because there's always some part of the world where these sites are being accessed. And of all those pairwise similarities, you don't actually use all of them, of course, because you're only going to use them for items that the user has ranked. And here's some philosophy, which again I have to take on face value, that it is better to use items than users because the items are more stable than users. And you don't actually have to calculate all. If you have n items, you don't actually have to calculate n squared numbers because many of the items are don't have any rankings users in common. So that's there for them. There is no similarity at all. And you can also obviously do various restrictions and which can cut out even more cases. And here, this is some remarks. This is actually for both item-based or user-based. Question is how you do rank ratings or rankings. You just, if you go to any of these sites, you can see how they do it. They use stars or some sort of way of doing this. Likert is famous for having defined a whole set of response scales. I mean, the 1 to 3 is bad, good, best, or something like that, and 1 to 7 goes from violently disliked to violently liked with various gradations in between, and so on. And so these numerical scales, which do not have much granularity, turned out to be reasonably successful because it's probably true that most users really can't rank terribly accurately them better than this 1 to 5 or similar type of scale. So in movies, I gather that the 10-point scale was accepted. There is something we mentioned earlier, the Joker website, and we discussed that in the previous talk. And there they actually had a continuous scale and some sort of input bar. And obviously, we also can use rankings of different parts of the item. If you go to audible.com, where you rank books, which I sometimes do, you will separately rank the story, the reader, and so on. And so there are multiple rankings which you can make. Although again, you often only look at the overall ranking, unless there's some particular case where, say, the reader of the book is violently negative, is given a negative review, which could then drag down the overall review. So you may wish to have this, but this is probably, again, I doubt if it affects things too much. Although users are not willing to rank many items, and people like me rarely rank anything, and we ignore my emails from Amazon telling me to rank how a particular marketplace vendor performed. I rarely respond to that, so I'm not helping Amazon give feedback to its users. But there are so many users these sites have that they get lots and lots of rankings. And I consider it one of the miracles of the internet that I wouldn't have predicted that in a very good example of big data and a data-oriented approach, that these rankings are an enormously powerful way of making very precise statements as to which items a user would like. And that's not what I would have guessed, but because I would have guessed the more obvious content-based recommendations where you looked at the actual physical features of an item and use that to try to predict what other items the user would like. And here's some comments on ratings. There are the times when you actually click and say this is 1 star through 5 stars, but just the fact that you click and go to a particular buyer, say at Amazon, sorry, I should say seller on Amazon, is already telling you something. And also, when I spend a long time on a page, I probably like it better than when I immediately dismiss it and go to another page. And so there are a lot of so-called implicit ratings. Sometimes there's a called context. And as they point out here, the fact that I bought a book doesn't mean I liked it. Often I buy a book which I don't actually like so much. So the characteristic which works, if I buy a book I don't like, I don't buy another book of that author. So you can look at some implicit rating. How many authors do I buy multiple books of? That is a strong statement that I like those books. Now we here have, remember that we're doing big data, some aspects of big data doesn't have so much data, so that's worth discussing. Obviously, when an item suddenly arrives, we not so easy to recommend it because it has no rankings, and you either have you sort of have a sort of forced march where you actually drag users along to rate these items. You can also use, of course, the content-based approach initially, and then gradually phase in the ranking-based approach. There are presumably always better algorithms. We remember with Netflix, I think the winning algorithm combined 100 different approaches or some number like that. And that's obviously an area of research. Again, I suspect most of this research is going on within Amazon and Netflix and so on, and they don't tell you what they're doing. One approach which is illustrated on the next slide is transitivity, which says that if you have a set of users near B near A, and another set of users C near B, probably C near A, and that could be a non-trivial deduction because A and some of the users in C may not have the rankings in common to allow a direct calculation. However, there may be rankings in common to allow you to know that A is near B, and a different set of rankings in common to know that B is near C. So this is a very interesting feature of the sparseness of these vectors, because this transitivity is actually trivial if the vectors are all fully populated. It's just a property of distances. If A is near B and B is near C, and these are real distances, then A is pretty near C. And that's the triangle inequality. But we know that triangle inequality is definitely not true and cannot be used directly. So you have to have some slightly non-trivial assumptions to use it here. So here's the recursive collaborative filtering algorithm briefly discussed. And this is an example of transitivity where you effectively apply collaborative filtering recursively, so that if we have this example here where user 1 is near Alice and they have a strong similarity, but unfortunately we can't use user 1 directly to help Alice rank item 5, we may be able to find other users near user 1 where they have rankings in common, so we can actually get a ranking of, estimate the ranking of user 1, and then use that ranking of user 1 to help Alice. There, the whole point is that we might have identified a set of wonderful users near Alice, but those users are not directly ranked to some of the items we care about, but those users near Alice have friends, or whatever you want to call these people are near them, who have done relevant rankings. Obviously, this can be applied in very complicated iterative fashions. It says here recursive. Recursion or iteration sort of mean the same thing here.